When we talk about the merger of the orbitals to form the molecular orbitals, we can have any kind of possible arrangements. We can have any kind of possible attraction. We can have any kind of possible mergings. Now, it could be the 1s merging with 1s, it could be 1s merging with 2s, it could be 1s merging with 2p, it could be 1s merging with 3p, it could be 2s merging with 2p, and so on and so forth. Now, there is
Yeah.
also a possibility that there is not a necessity that two orbitals have to merge with each other. There is a possibility that three orbitals can also merge with each other. 4, 5, 6, 100,000, million, billion, any number of orbitals can merge with each other. And therefore, we have an infinite possibility, infinite arrangements which are possible. Since we have infinite arrangements, we obviously cannot do all of them. We can do only a few of them. And when we understand that we are able to do only a few of them, we restrict ourselves a lot. What we are going to do is we are going to talk about only diatomic molecules. That is, we are going to talk about the molecules which have only two atoms. So we are going to talk about only diatomic molecules. And second thing, not only we are going to talk about the diatomic molecules, we are going to talk about the diatomic molecules which have only identical atoms. So we are going to actually talk about something what we know as homonuclear diatomic molecules. So we are going to talk about homonuclear diatomic molecules. Now, when we are talking about homonuclear diatomic molecules, there also we are going to have huge number of possibilities. We are going to have huge number of arrangements. What we are going to do is we are going to talk about only homonuclear diatomic molecules till atomic number 10. So when we are talking about homonuclear diatomic molecules at atomic number 10, we are just going to talk about the arrangement from hydrogen till neon. We are not going to go beyond neon. So it becomes
Yes,
homonuclear
sir.
diatomic molecules up till neon only. And when we are going to talk about this arrangement, we are going to have just something like 1s with 1s. Excuse me. We have the overlap of 2s with 2s, and we have the overlap of 2p with 2p. That's it. We are not going to talk about any further overlaps.
Yes, sir.
So that is what we have as homonuclear diatomic molecules till atomic number 10. Okay. Now, having talked about these homonuclear diatomic molecules, now let us talk about how the overlap actually takes place. If you understand, if you remember, we have already done the overlap of the 1s with 1s. Okay.
Yes, sir.
Rohan, I believe I had sent you the link on WhatsApp of the previous class, that half an hour class. It should
Yeah.
be with you. Okay, have a look at that. And today's class also is being recorded. Now, we are going to talk about now the overlap of the orbitals. First of all, we are going to talk about the overlap of the 1s orbital with 1s. We actually have done it, but still we are going to do it again. Can you see it till here?
Yes, sir.
Okay, so we have the 1s orbitals. Here we have one of the 1s orbital, here we have another 1s orbital. These two orbitals overlap with each other. So this is the overlap of s with s. Now there are two kinds of overlap. One overlap is going to be of the region which are common inside, which are going to overlap with each other. When these orbitals overlap, they are going to give us a region like this. This region would be formed. Okay. And
Yes, sir.
then if we talk about the overlap of these parts which are behind the nuclei, the overlap would go like this.
Okay.
This. Okay. So this is the overlap of 1s with 1s or s with s. 2s overlap is also going to be the same. It's not going to be different anyway. If we talk
Yeah.
about the second overlap, that is the overlap of P with P. We can have this as the axis. Here we have one p orbital. This is going to be the 2p orbital. And here we have the 2p orbital. Now this is what we call as the pp axial overlap. This is going to be on the axis. Now when the P and P or axial overlap is going to take place, whichever axis you wish, you can take it to be. You can take it X, you can take it Y, you can take it Z axis. If I take it the Z axis, then in that case, this is the overlap of PZ orbital with PZ orbital. And obviously this is 2PZ with 2PZ. Now these two orbitals, when they overlap, they are obviously going to form two orbitals. Now when I talk about those two orbitals, I'm going to get one orbital would turn out to be like this. Another orbital is going to be like this. This is the PP axial overlap. Now we can talk about the third overlap. Now this is going to be the overlap of p orbital with a p orbital, and that is going to be the parallel overlap. So if we talk about the parallel overlap, we are going to have the orbital. One orbital is like this. This is what we call as parallel or lateral overlap. So if I talk about the parallel or the lateral overlap, here we are going to have the overlap in this manner. There's going to be a region like this. There's another region going to be like this. Here, the regions are like these.
Sir, what are those red and green ones?
Green is the axis, blue is the orbitals or after
Yeah.
overlap. These red are the orbitals which are formed by these regions.
Okay.
This, and this region. They give us the red parts.
Yes, sir.
Now, when I talk about these orbitals, what I find is that there are two kind of orbitals. That is, as such we have four kind of orbitals, but we can say two kind of orbitals. That is, there are certain orbitals in which the internuclear axis has the maximum electron density. Here we have the maximum electron density on the internuclear axis. Here we have the maximum electron density on the internuclear axis. Here and here on the internuclear axis. But here what we find as the electron density on the internuclear axis is the minimum.
Okay.
Clear?
Yes, sir. Yes, sir.
Okay. So we have two kind of orbitals. One orbital where the electron density is on the internuclear axis, and one orbital where the internuclear axis has the minimum electron density. Here, these
Yes, sir.
orbitals in which the electron density is on the internuclear axis. The orbitals in which the electron density is on the internuclear axis are termed the sigma orbitals, and these form the sigma bonds. So write it. the orbitals in which the electron density the orbitals in which the electron density is on the internuclear axis. The orbitals in which the electron density is the maximum on the internuclear axis are termed the sigma bonds, are termed the sigma orbitals, and they form the sigma bonds.
Yes, sir.
Is that clear? That is
Yeah.
what we have as sigma orbitals, and that's what we call as sigma bonds. Now we can talk about these orbitals also, where the internuclear axis is actually the node, where the electron probability is the minimum on the internuclear axis. Let's talk about those orbitals also. Now these orbitals, these are called the sigma orbital. This is 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 the sigma s. This is the sigma s. This is the sigma 2pz. This is the sigma 2pz. Okay. Now let's write the definition for these. Write it.
Yes, sir.
The orbitals in which the internuclear axis is a part of nodal region. The orbitals in which the internuclear axis is a part of nodal region, that is, it has the minimum electron density. That is, it has a minimum electron density, are termed pi orbitals, and they form pi bonds. Is that okay?
Yes, sir.
So this orbital could be pi 2px, or it could be pi 2py. Similarly, this could be pi 2px, or it could be pi 2py.
So 1 second. Yes, sir.
Fine. So that is what we have as pi 2px or pi 2py. This is what we have as sigma 2pz and sigma 2py, sigma 2pz. Now, we can distinguish these orbital in one more way. When I talk about this orbital, here the electron density is the maximum between the two nuclei, that is in the region between the nuclei. Here when you talk about the region between the nuclei, that is having the minimum electron density, that is, it is a node. Here we have the maximum electron density in the region between the nuclei. Here again, the region between the nuclei is a node. Here again, we have the maximum electron density between the nuclei, and here again, the region between the nuclei is a node. So
Yeah.
here again, we can distinguish between the orbitals. Let's write the definition once again.
Yeah.
The orbitals in which the electron density, the orbitals in which the electron density is the maximum. Electron density is the maximum in the region between the nuclei. Electron density is the maximum in the region between the nuclei. Are termed bonding molecular orbitals. These are termed the bonding molecular orbitals. That means this is sigma s bonding, this is the pi, sigma 2pz bonding, this is pi 2px or pi 2py bonding. Okay?
Yes, sir.
Okay. By the next definition, the orbitals in which the electron density, the orbitals in which the electron density is the minimum in the region between the nuclei. In the region between the nuclei. That is, the region between the nuclei, that is, the region between the nuclei is a node. Region between the nuclei is a node. Are termed antibonding orbitals. Are termed antibonding orbitals. These are designated by putting a star on the name of the orbital. These are designated by putting a star on the name of the orbital.
Yes, sir.
Fine. So here we write it at sigma s star. This is sigma 2pz star. This is pi 2px star or pi 2py star. Okay. So here we have put a star on the name.
Yes, sir.
Fine. So that is how we have designated the sigma and the pi orbital, the bonding and the antibonding orbital. Now what we find is that many a times and most of the times we find some sign in the orbitals. We get the plus and the minus sign, something like plus and the minus. Here we get plus, here we get a plus and the minus. Here we get plus and here we get the minus. And let us say here we get the plus, here we get the minus, here we get the plus, here we get the minus. Now what exactly these plus and minus denote? These
So
plus
one
and
second.
minus.
Sir, for the third one, how many, where are the pluses, sir, for the parallel thing?
We have the plus at the top and the bottom, minus at the bottom. See,
Okay.
here we have the plus, here we have the minus. Here we have the plus, here we have the minus, here we have the plus, here we have the minus.
Yeah.
Plus, minus, plus, minus, plus, minus, plus, plus, minus, plus, plus, minus.
Okay.
Okay. Now these signs, they have absolutely nothing to do with the probability. These have nothing to do with the energy. These have nothing to do with the charge. These plus and the minus signs simply talk about the sign of the wave function. Please remember, these are nothing but the wave functions. So whatever sign we are writing, these are the signs of the wave function. So these plus and the minus, they represent the sign of the wave function in that region. So just write it.
Yes, sir.
The plus and the minus sign, the plus and the minus sign written in the orbital. The plus and the minus sign written in the orbital represent the sign of the wave function, represent the sign of the wave function in that region. Is that clear?
Yes,
So
sir.
that is what we have as the plus and the minus sign. That's what it denotes. Okay.
Yeah.
Now, talking a little further. So that is what we have as the plus and the minus sign. Now we talk about a little one more thing. We talk about the center of the symmetry. When you talk about the center of symmetry, it would mean that we move from one part to another part. Well, what we do is we start from the center of the orbital and we move in a certain direction to a certain distance. And then we move exact opposite direction with the same distance. If we find the identical region, we
Sir, I'm not
say,
able to see what you wrote, sir.
okay, see, what I did was I moved from this position to this position and we move from this position again to this position. That is, I move from the center of the bond, I move in a particular direction to a certain distance. And then I move from the center of the bond in the opposite direction to the same distance.
Yes, sir.
So if I get the same region, I would say that the orbital is symmetrical and this point is the center of symmetry. So just write
Okay.
it. If from the center of the orbital, if from the center of the orbital, we move in a certain direction, move in a certain direction to a specific distance, to a specific distance, and again from the center, again from the center, in the opposite direction, in the opposite direction, for exactly the same distance for exactly the same distance then if we get the same, then if we get the same, then if we get the same sign, we say, if we get the same sign, we say the orbital is symmetric. Orbital is symmetric. And the point is, the center, and the point is the center of symmetry.
Yes, sir.
And the point is the center of symmetry. Is that clear? So
Yes, sir.
if I talk about this sigma s, here we find if we move in this direction, we have both directions identical. So I would say that sigma bonding is symmetrical. If I talk
Yeah.
about the sigma antibonding, here we have the negative, here we have the positive. So here we are getting a different sign. So sigma antibonding of S becomes unsymmetric. Sigma bonding turns out to be symmetric and sigma antibonding turns out to be unsymmetric. Similarly, in the case of P, this comes out to be symmetric. The antibonding comes out to be unsymmetric. But when we talk about the pi orbitals are peculiar. Here what we find is if I move in this direction, this is positive. If I move in this direction, it is negative. So what I find is that pi 2px or pi 2py is actually unsymmetric. Whereas if I talk about the antibonding orbital, it is actually symmetric. So what do we get? We get sigma bonding S is symmetric. Sigma antibonding S is unsymmetric. Sigma bonding P is symmetric. Sigma antibonding P is unsymmetric.
Yes, sir. So sigma bonding is symmetric.
And sigma antibonding is unsymmetric.
Okay.
Pi bonding is unsymmetric, while pi antibonding is symmetric.
Yes, sir.
Is that clear?
Yeah.
Okay. So that's what we talk about symmetric or unsymmetric. That is what we talk about the orbitals. Now, this is the orbitals. These are the diagrams of the orbitals. Now, these orbitals are supposed to accommodate the electrons. And these orbitals, when they're supposed to accommodate the electrons, I need to take care of the normal orbital filling principles. And what are those normal orbital filling principles? The Aufbau principle? which simply
Yeah.
says the Pauli's exclusion principle, the Aufbau principle, the Hund's rule of maximum spin multiplicity.
Yes, sir.
And that first rule says the lowest energy orbital is filled first.
Yeah.
Fine. So lowest energy orbital is filled first. So here, when we talk about the lowest energy orbital being filled first, we need to know what is the order of energy of the orbitals.
Yeah.
Okay. So when I talk about the order of filling up the energy and we talk about the orbitals, the simple thing is, let's make the graph of the energy. Let's make the graph of the energy of the orbitals.
Okay.
Clear? So here we make the graph. Please remember, this is just a graph of the energy. This is the energy. This is the energy of one atom. This is the energy of another atom.
Yes, sir.
Okay. And I'm just going to plot the energy. In the books, they might write boxes. They make the square. They make the rectangle. They make the ovals. They make the circles. Doesn't make a difference. Whatever you like, make it. These
Yes,
are
sir.
just giving us the energy, relative energy of the orbitals. Something like here it is going to be the 1s orbital. Since we are talking about homonuclear diatomic molecules, the two atoms are going to have exactly the same energy. So this also is going to be 1s. Here
Sir,
we are
what is
going,
on left side?
left side is the energy of one atom and the right hand side the energy of the another atom.
Okay, okay.
Okay. Both are homonuclear, so their energies are going to be same.
Yeah.
Okay. This is going to be 2s. This again is going to be 2s. Here
Yes,
we are
sir.
going to have the three 2p orbitals. They are going to be of the same energy. They are degenerate. And here again, we are going to have three 2p orbitals.
Yeah.
Okay. So when we talk about these 1s and the 1s orbital, the 1s and the 1s orbital merge with each other to form two orbitals. One is what we have as the bonding orbital, another which we have the antibonding orbital.
Yeah.
One orbital is going to have a lower energy than both the orbitals mixing with each other,
Yes,
while the
sir.
other orbital is going to have a higher energy as compared to both the orbitals which are mixing with each other.
Yes, sir.
So here it's going to be an increase in energy. Here it's going to be a decrease in energy. We did it. One orbital is
Yeah,
going to
yeah.
have higher energy and one is going to be of lower energy. That you would have written in your copy itself. So
Yes,
here,
sir.
this is the increase, this is the decrease. So this is what we have as sigma 1s and this is what we have as sigma star 1s.
Yes, sir.
Now here we have 2s orbitals. When we talk about 2s orbital, they are also going to merge with each other. One is going to be of a lower energy, another one is going to be of the higher energy.
Yeah.
These orbitals are merging with each other to form the two orbitals. Now this is going to be sigma 2s and this is going to be sigma star 2s.
Yes, sir.
Is that clear?
Yes, sir.
Okay, fine. Now Rohan, I told you what are the two factors which are required for the orbitals to merge with each other. There are
Yes, sir.
two necessary conditions for the orbitals to mix with each other.
Yeah.
And those two conditions are the very first condition, the orbitals must have a common probability region.
Yeah.
And second, they must have similar energy.
Yes, sir.
Correct?
Yeah.
That's what we had written. For any two orbitals to merge with each other, they must satisfy two conditions. One, they must have a common probability region. And second, they must have the similar energy. That is the two conditions they must satisfy.
Yes, sir.
Now, more efficient is the overlap. That is, more similar is the energy, more overlap is there, more is the change in energy. When they have efficient overlap, then the increase in energy is also high, the decrease in energy is also high, and the gap between the two orbitals which are formed increases. As the overlap becomes less, or the whatever could be the reason, maybe the energy difference is already very high, or maybe the overlap, the region of probability is not enough. The rise
Yes, sir.
becomes low and fall also becomes low. Is that clear?
Okay. Yes,
So
sir.
when we talk about the sigma orbital formation, the sigma orbital formation of the 2p, the region which are overlapping is quite high.
Yeah.
So when I make the sigma orbitals, let us say I talk about the merging of the three p orbitals, 1, 2, 3, 1, 2, 3, the three p orbitals, then what should happen? What should happen is that when the sigma orbital formation is taking place, the orbital fall should be an extremely high one. The rise also should be an extremely high one. This is going to be the sigma 2pz. This is sigma 2pz star.
So I'm more able to see the top part because there's something on screen here.
There's something on screen here.
Yeah, on my screen, like there's a box. Like two people have joined in all.
You can make it full screen.
Yeah, so I'm in full screen. Oh, I made it small. Yes, sir. So
Can you see
two
it now?
PZ star.
Can you see it now?
Yeah,
Okay.
yeah.
So that's what we have as sigma 2pz. Now, when we talk
Yes,
about the
sir.
pi orbitals, the overlap region is quite small. Here, this is the only going to be the overlap region. This is the only going to be the overlap region. Since the overlap region is small, therefore the rise and the fall in the pi orbitals also is going to be small.
Oh, yes,
So
sir.
here, these are going to be the two pi orbitals. This is going to be pi 2px. This is going to be pi 2py. This is going to be pi star 2px. And this is going to be pi star 2py.
Yes, sir.
Okay. So that is what the arrangement should be there when we talk about the p orbitals.
Yes, sir.
Now, Rohan, see one more thing, one very, very important thing. If I talk about sigma s and I talk about sigma p, can you see that they have the same region of probability?
Yeah, yes, sir.
The sigma s orbital and sigma p orbital have the identical region of probability.
Yeah.
Now, if the energy difference between them is not too large, there would be an overlap of the sigma 2s and sigma 2p orbitals.
Yeah.
So, here we are having the sigma star, and this is sigma 2s orbital. This is sigma star 2s orbital. This is the 2s. This is the 2s. These are going to overlap. Now the sigma 2s is going to overlap with sigma 2pz. Okay. The
Yes, sir.
sigma 2s overlaps with sigma 2pz. What happens is this sigma 2s is going to actually go lower in energy. Somehow it's going to come here.
Yes,
Okay,
sir.
this is going lower in energy. And the sigma 2pz, which should be a lower energy orbital, it actually rises in energy and maybe goes to this position.
Okay.
Okay, so this becomes sigma 2pz. Now what happens? A peculiar thing happens. These pi orbitals are still at the same position. The pi orbitals are still at the same position. The sigma orbital, which should have been here, actually rises up so as to become of higher energy than pi 2py or pi 2px. Now, why has this happened? Because the sigma 2pz has merged with sigma 2s. They have identical region of probability. And this is what we termed as SP mixing.
Oh, fine, sir.
This is what we term as SP mixing. So here, but the higher energy orbital remains the same. Sigma star 2pz remains at the same position. It's not going to come down.
Yes, sir.
This doesn't change. This is again pi 2px star pi 2py star.
Yes, sir.
Okay,
Yeah.
so here we have pi 2px and pi 2py sigma 2pz. Now, this is because of SP mixing. This has taken place because of the SP mixing. Now, you need to understand as we are moving across the period, let's say from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, as we are moving across the period, the energy gap between the 2s and 2p orbitals increase.
Yes, sir.
As the energy gap increases, the chances of these to overlap with each other is going to decrease. So write the statement. On moving across the period, on moving across the period, the energy gap on moving across the period, the energy gap between the energy gap between the orbitals belonging to the same shell increases. That is, on moving from lithium to fluorine, that is, on moving from lithium to fluorine, the energy gap between 2s and the 2p, energy gap between the 2s and 2p subshell, energy gap between 2s and 2p subshell increases from 200 kilojoules per mole 200 kilojoules per mole to 2000 kilojoules 2500 kilojoules to 2500 kilojoules per mole. Full stop.
Yes, sir.
This makes the overlap of two s and 2p orbital that is sp that is the sp mixing difficult. Fine.
Yes, sir.
Okay. Now what we find is that till nitrogen, the sp mixing is effective enough to make the sigma orbital energy higher than pi orbital energy. But the moment we move to oxygen, the sp mixing is not significant enough and the sigma energy is actually lower than pi. So beyond oxygen, it behaves as if the sp mixing does not take place. So just write it.
Oh,
Okay, write
yes,
it.
sir.
Till nitrogen, the sp mixing till nitrogen, the sp mixing is effective enough till nitrogen sp mixing is effective enough to make the energy of the the sigma 2p orbital, to make the energy of sigma 2p orbital higher than pi 2p orbital. Full stop. Beyond nitrogen, beyond nitrogen, the sp mixing is not effective. The sp mixing is not effective and the inversion of energy what did I say? It behaves
So
as if
the inversion of energy.
does not take place. So what we find is that the sigma has a lower energy and pi has the higher energy. So this is the diagram from O2, F2, Ne2. Now this is the diagram till nitrogen. Is that clear, Rohan?
Yes, sir.
Okay, Rohan, what have you done in the Fiji class?
So we, I think we did till hybridization.